Well, in this talk, I will illustrate the interplay between free will and quantum physics. Actually, I will highlight that quantum physics is assuming free will as a basic principle of science. Second, I will stress that the material visible world cannot be explained exclusively by material visible principles. And finally, I will argue that there is not such a thing like pure randomness in the world. Randomness as in the sense of lack of control. Randomness and non-material control, control coming from outside space-time, are inseparably together. To begin with, I would like to explain you in a very simple way the concept of quantum non-locality. That, in my opinion, is today we could say the crucial notion in quantum physics, much more relevant than in determinism. We have here laser source emitting light, and this here is half silvered mirror, a beam splitter, so that 50% of the light goes transmitted and 50% goes reflected. If we put here two detectors, this detector will fire 50% of the time, and this one will fire 50% of the time. So each detector will count 50% of the counts produced by the light particles. Well, now suppose we build an interferometer this way. Here we put full silver mirrors to guide the light, so that the light is guided to this detector here and to this detector here. For the moment, here we put nothing. Then, how would you say? How many % of the light get we here in this detector? You will say, well, the same than before, so 50% and 50% here. Well, now suppose that we put here another silvered mirrors like this one here, so that exactly another beam splitter here. The question is now how many percent of the light, of the counts, we have in this detector and how many we have in this one. So, if we are reasoning with the model of particles, we will say here is coming 50%, and then here you get 25% and 25%, and the same for the other path, so that you get here 25% and here 25%. At the end, you would say we get here 50% and 50% again. Well, the result of the experiment refutes this explanation. Actually, it is an interferometer, a Mach-Zehnder interferometer, and the experiment shows that we get here 100% and here 0%. How is this possible? Well, the explanation was given with the model of waves, stating that light behaves like waves. So that if you have a wave coming this way, then this wave will be partially transmitted and partially reflected. And now you have another wave coming this way. And this wave will again be partially transmitted and partially reflected. But there is a difference, because here the red wave is transmitted and here reflected, and the other one is reflected and transmitted. So they come out with the same phase. Okay? And then we have constructive interference. For the other path, you have reflection and you have reflection here and reflection, and here you have transmission and transmission. This, I will not enter details, produce that the waves are coming in opposite phase. One is coming so and the other is coming so. So you have here destructive interference, and then you get 0%. Okay? That is our experimental facts. Now we can go ahead and suppose that we can change a bit the path of this, of the length of this path, by a device. We could put here so mirrors. So this device allows me to change the length of this path. What happens then? Then it is quite interesting. Suppose we say this is the detector 1 and this is the detector 0. So we here probably we can represent here how the counting rates in the detectors change. If you put here the phase and here the counting rate, okay, then for detector 1 you are going at the beginning 100%, and then you get a sine curve like this, and for the other one you get the opposite. It starts with 0, it goes to 100, and again to 0, and so on. Okay, so that is what we get from the experiment. What means this? This means that really it seems that light is behaving according to the model of waves. But that is not the whole story, because if light would be exclusively behaving like waves, then we get the following prediction. Take, for instance, the case where we have here, for instance, here 60%, and here 40%. Okay? Then this means this detector, all detectors are firing. Both detectors are receiving waves, information, so they are firing together. And this one will fire a bit stronger and this a bit weaker. But all the time they have to fire together because waves are arriving to both detectors. And this would be the case even if we work with very weak light, because you have waves here and waves here. Okay? But that is not the case. When you diminish the intensity of light, then you get either this detector fires and this doesn't fire, or the opposite. This fire and this doesn't fire. So that is actually amazing, because you see what happens here is that both detectors are working, are functioning according to the information of the two paths. But at the moment of firing, they have to have a coordination. Some agency is coordinating these two detectors so that if the one fires, the other doesn't fire, and vice versa. Well, this idea was already so old, the beginnings of quantum physics in the year 1927 was exposed in the Solvay Congress by the Copenhagen group, the Copenhagen School, also people like Niels Bohr, Heisenberg, Werner Heisenberg, Max Born, and then Einstein was quite upset. Why? Because if things are this way, when these two detectors are near to each other, suppose we can put this part of the experiment we put here, so we can put these two detectors far away from each other so that there is no time for any communication between them. This means that if there is a coordination between these two detectors quite far away from each other, then this communication should happen faster than light. And that is why Einstein was quite upset and against quantum physics. He said, look, this cannot be true, this cannot, and therefore quantum physics is incomplete, and it is actually wrong. It has to be completed. This was the position of Einstein. So this experiment, quite simple one, is amazingly has not been done till quite recently. Also, the other sophisticated experiments have been done, but this one has been finished some weeks ago in the lab at Geneva of quantum optics, and we hope to publish soon the results in the archive. But you can see, suppose that we put these detectors far away, then what will happen? Each detector will fire at random, without coordination. Then you will get 50% of the times you will get when 0, also detector 0, detector, excuse me, what? This detector fires here, and this detector doesn't fire. 50% of the time you get the other case, and 50% of the time you get the two detectors fire, and 50% of the time you get no count in each detector. Okay? Also, I would say the first number here means whether detector 1 fires or not, and the second one whether detector 0 fires or not. So you will get this prediction if there is no coordination when they are far away, and the experiment shows that this is not the case. This case doesn't exist. So actually what you get is here 50% and here 50%. Like when the two detectors are near to each other. Okay? So this means that even when the two detectors are far away, we have this non-local coordination. What means this? Actually, it means that there is here some principle coordinating these two detectors which cannot be explained by means of signals of light. You cannot explain, because here it would require a coordination which goes faster than light. So we have here then a phenomenon where there is some agency, some principle coordinating these two detectors which comes from outside space-time. And this is the same as to say, well, it is not material, but it is in the sense that no material in the sense that it is not observable. It is not something that you can directly detect. It is not visible, so to speak. Once again, you have visible results, detections, that are ruled by some invisible principle. That is the statement. We come now to the, before I go to the second part, I would like to show you that an interesting, quite recent result too, is that this kind of quantum phenomena, you can call this interference or quantum coherence, this is entering now the domain of biology. For instance, to explain photosynthesis, there are now works, experimental works showing that you have to have some kind of quantum interference or coherence. Things are going like this, quite roughly and quite simple explained. Photosynthesis, you have in the leaves of the plants certain so-called light harvesting complexes, are large complexes with many cells and molecules, and when light arrives here, when photon of light hits here a molecule, then this molecule ejects an electron and becomes charged with a positive charge and a negative one. So you have the molecule, the electron goes away, and then the molecule remains positively charged, but the electron and the molecule remain bound. This is called an exciton. It is like a molecule which is prepared to give energy. But to do this molecule has to reach here, this center. That is the reaction center. Okay? And what we are discovering, what we are observing, are phenomena that we know that to go from here to here, it is like a random walk. You would come, probably hit here and go away, or come here, 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 and probably go away again. So if you try to explain how this exciton reaches this reaction center to produce the photosynthesis, to produce the sugars, then if you try to explain this by classical means of a random walk, you get a very low efficiency. However, we know that this process is quite efficient, to a great efficiency of 99%. How can we have such a great efficiency that is not understandable by classical means? It's like if you shoot a ball through a forest, the probability that the ball reaches the other edge of the forest is practically small, very small. And however, we have this big efficiency here. Well, and that is because there is an interplay of quantum coherence, quantum interference, and the classical decoherence phenomena. It is this interplay that allows this big efficiency. I would like to illustrate this with this idea. This is the reaction center, okay? And here you have the photons arriving. And you see, then efficiency is very little. What the quantum interference produce here is like a funnel. It is the quantum interference allows makes that the energy is funneled to the reaction center. So you see, then it is much bigger efficiency. Well, the interesting point is, what I am saying is that this funnel, this you can say this quantum funnel, is not material. It's not in the sense that it's not visible. It's not something tangible. It's not something that is in space and time and you can access. It is not something that you can access. And you can say, well, it is a law of nature, sure, but this law of nature is not registered in space and time. Okay, that is, so this kind of phenomena are now becoming important also. It is not very at the beginning, but it seems that, for instance, in plants, also in ion channels, we have quantum interference playing a role. The second point I will stress is that we have said that if we would not have this coordination here between this this non-local coordination coming from outside the space-time, then 25% of the times you will have both detectors firing. One count here and one count here. And in 50% of the times, 0 counts here and 0 counts here. That is to say that energy is not conserved. Because if you have here one photon arriving, it is a packet of energy, if the detectors are not coordinated, then sometimes would fire both together. So you would have one photon and 2 counts. And sometimes you would have one photon and no count, neither here nor here. And what this means that the energy would be conserved in the average, but not in each single quantum event. So you see that the most material principle of physics, the conservation of energy, is related to non-locality. This means to non-material control. You can say something coming from outside the space-time. So once again, the visible, the principle rolling the visible world requires invisible, unobservable influences. We come to the third part of the talk, and it is the unity of randomness and control. Once again, we get one count here and no count here, or one count here and no count here. We note, for instance, if detector 1 fires, we write here 1. If detector 0 fires, we write 0, 0, 1, 0, 1, 1, 0, and so on. Okay? So this is simply the sequence of the outcomes we can get here in an experiment. What quantum physics tells us is the percent, the rate of ones that we have in this sequence, or the rate of the zeros we get in the sequence. That is what quantum physics tells us. However, the order of these bits, about this, physics says nothing. So that actually in the lab we will get here something that we call random, in the sense that it looks as meaningless. But be careful, because even when you have this and you say there is no meaning here, but there is already this control in order to coordinate the two detectors. So you have here not pure randomness in the sense of Leco control. You have something which is not meaningful for us, but there is here already a control coming from outside space-time. And what is more is that quantum physics is perfectly compatible with the idea that you could get here the Divina Commedia digitalized. This would be perfectly compatible with quantum physics. Okay? So you say, well, but in the lab we don't get here the Divina Commedia. That is true. But I say we have human brains, and the human brains are, in a sense, physical devices, working also according to physical principles. And when I am speaking now to you, I am producing outcomes. Outcomes that we could digitalize, and then we have here outcomes which have a meaning. And this is perfectly compatible with quantum physics. Nevertheless, also in this case, would you say, well, we have here pure intentional behavior, we can have a behavior also pure consciousness? Are human brains devices which can work all the time according to a free-willed pattern? Can we say, are we pure consciousness? in the sense, I understand, can I indefinitely produce a behavior which is intentional and according to what I wish to produce? Yes? What happens with sleep? Okay. Also, I would say that also in the case of the human brain, we have not always, all the time, a behavior which is meaningful. But we have also, because of this fundamental principle of the cycle, wake, sleep, also there you have a high level of conscious behavior, but also combined with random behavior. So we have here, this is what I want to stress, we have at the level of device like this in the lab, you can say you have a high amount or a high level of randomness, but also control, non-material control, coming from outside the space-time. And you have, in the case of devices like the human brains, you have a high level of conscious behavior, but also combined with a behavior which is not intentional, which is to some extent random. That is what happens in sleep. I want to say still something, that this cycle of sleep and wake, I am not saying this is something that you explain by quantum physics, but I think personally that this is much more fundamental than quantum physics. Sleep is today a very poor understood phenomenon, and I think we have to work much more also to understand sleep in order to understand the basic roles of the basic physical roles of the universe. So here I would like to finish. We can now discuss the different points of the talk. Thank you very much.